All right, let's figure out the row space and the null space and the column space. We could do that by doing a row reduction. And I think we just need to, I don't know if we need to do one or two things. One step is to take the first row, multiply it by -1, add it to row 3. Got 1, 1, 1, 0, 1, 0, and then this is going to be 0, 1, 0. And then you just row 2 plus row 3 will get rid of that last row. So the row space is going to be the span of the two row vectors, the first two row vectors, and it looks like it's the same whether we take the original or the reduced one. And then the null, if we solve for this as if it was homogeneous, we got a free variable here in x3. So x3 is free. X2 looks like it's not dependent on x3, so x2 is equal to 0. And x1 is equal to minus x2 minus x3. 0 minus x3. And so if you look at that, it's -1, 0, +1. So the null of A is going to be the span of -1, 0, +1. And what we want to show is that the perp of row A is equal to the null A, which means row A and null A are supposed to be perpendicular complements of each other. So row A is a plane in R3. This is all in R3. And null A is a line in R3. And then those are supposed to be perpendicular to each other. So we check the basis vectors that we have, that 1, 1, 1 dotted with -1, 0, 1 is equal to, well, if we do the dot product, it's -1 plus 0 plus 1 is 0. So that checks out. And then 0, 1, 0 dotted with -1, 0, 1 is equal to 0 plus 0 plus 0. So there's really only two things to check here, because any linear combination of anything in the basis vectors in the row space would just be like A times 1, 1, 1 plus B times 0, 1, 0. And then if you dot that with a span, then we're going to get 0 anyway. So this checks out. And then we can do the same for the column of A. All right, so let's check the column. So we have free variables. We have a pivot in the first and second columns. And so we take the first and second columns of the original matrix, so that the column of A is going to be the span of 1, 0, 0 and 1, 1, 1. And so now we want to take the transpose and find the null space of that. So that's, we want to take the transpose, A transpose, and then take the null space of that. So let's take the transpose. AT is equal to 1, 1, 1, 0, 1, 0, 0, 2, 1. Oh, this is a 1. And then do the row reduction. So let's do the row reduction here. We'll do R1, -R1 plus R2, and then -R1 plus R3. So 1, 0, 1 is the top row, stays the same. The next one, 0, 1, 1. The next one, 0, 0, 0. Well, that was done. That was easy. So the null space of that if we take a look at this, we got a free variable here, and then so x3 is free, and then we have x2 is negative x3, and x1 is also negative x3. So negative 1, positive 1. And then that's your null space. The span of that is your null space. And then we can dot it with the, is that right? I'm doing the dot product in my head already, and it looks like the dot of 1, 1, 1 and negative 1, 1 is not equal to 0. I have to find the column space. I take a look at the, so I looked at the reduced row echelon form, and then I saw that there's pivots in the first and second columns. So I take the first and second columns here. Well, that's the column of A, and so that's what I'm looking for. And then what I'm saying is that the transpose of this should equal to this, which means if I dot any of these vectors in the basis of the column space with the basis of the null of the transpose, then it should be 0. Yes, call of A's from the original matrix, according to this. Oh, sorry. I should have been looking at this because I did one move here already. All right. Backtrack here. So this is 1, 0, 1. And 1, 1, 2. So you look at the pivots in your reduced form, and then you go to the original matrix, and the columns where the pivots were end up being your basis for the column space. Ali? Oh, okay. All right. So that looks better because when I dot them with the null of A of T is what I have here. So I want the null of A transpose, not negative. I don't know why there's a little minus sign there. So let's check. So I'll dot both of these. I could dot the linear combination, but it's just, if I want it to be 0, I could just dot them individually. So 101 dotted with this null space, -1, -1, 1. That's going to be -1 plus 0 plus 1, which is equal to 0. And then your second basis vector, 112, dotted with -1, -1, 1. gives me -1 plus -1 plus 2, which is also equal to 0. So this is not a proof, but this is a way to check that this theorem is actually true. Okay? Orthogonal complements. So according to this, the row and the null are orthogonal complements, and the column and the null of the transpose are orthogonal complements. So I'm out of room here, so let's write it down here. Complement. I don't know if this is an I or an E, so I'll put both and you guys figure it out. So if this is W and this is W perp, this is a perp. So row A, the orthogonal complement of row A is null A, and col A, the orthogonal complement of that is the null, not A itself, but the transpose of A. So these are orthogonal complements. And so that's what they mean by when they say row A complement, or the perp. That's what they mean. Okay? Any questions? All right. So that is going to lead us to the discussion that you guys watched a video for. So I'm not going to go through this in detail. I just kind of highlight a few things here. Going through the notes, we have the orthogonal set. So we talked about orthogonal vectors. That's when two vectors dotted, and we'll just use dot product. And, technically and abstractly, we're using the inner product, but we'll just leave the polynomial discussion out of this and just stick with vectors in Rn. So I'll use the dot product. So when we take the dot product of two orthogonal vectors, you're going to get 0, and then we extended that discussion to orthogonal spaces. And now those orthogonal spaces, or those orthogonal sets, are actually subsets of Rn, so of subspaces. So here are a couple of definitions. An orthogonal set is a set of vectors where everything is orthogonal to each other. Okay, so if I take two of these vectors that are not the same vector, that's when the I is not equal to J business. If I take two of them that are not the same, I dot them, I'm going to get 0. All right. Theorem 4 says that if I have an orthogonal set of vectors, then necessarily, because they're all orthogonal to each other, then those are all linearly independent. And because they're linearly independent set of vectors, they actually form a subspace. So the span of all those vectors forms a subspace. Remember the forms of basis, or they make up a basis for a subspace. Remember the definition of a basis is that the set of vectors have to be linearly independent, and then they span something. So they automatically span themselves into a subspace, and since they're all linearly independent, they are a basis. Oh, and this example that I had in the notes, because they're a basis, then we should be able to get to anything in that subspace. Now, in this example, in R3, I have 3 orthogonal vectors. Now, because they're orthogonal, they're linearly independent. Because there's 3 linearly independent vectors in R3, they must span all of R3, the whole 3-dimensional all of R3. And because they span all of R3, I can randomly pick any x that I want, any vector in R3, and I can write those 3 vectors as a linear combination of those 3 vectors to make it equal to whatever random vector that I chose. And one way to do that is to make a matrix out of this and then row reduce and do that kind of stuff, right? And that's how we got, or that's how they got the C1, C2, and C3. And we'll see in Theorem 5 that there's another way to do that. All right, orthogonal basis. This set of, if you have a basis for a subspace and then they happen to be perpendicular to each other, then it's called an orthogonal basis. So this is the theorem. If you have a set of orthogonal bases as a subspace of W, then any vector in that subspace can be written as a linear combination of those basis vectors. But not only that, now they gave us a formula to figure out what each of those weights are equal to. So each of those weights turned out to be the dot product of the vector that you're looking for with with the weights that you're dealing with, the vector, divided by the vector dotted with itself. And if that looks familiar, it is because it's the projection formula. So one way to think about this is that you're projecting y onto one of those vectors. Yeah, so these weights are really just the projection formula onto the projection formula onto each of those orthogonal vectors. Yeah, we'll see. So if I use that formula, I'm going to get the same weights as I got from previously. I didn't show the work here. I didn't show the work here to figure out what this is, but I think I used MATLAB or something in a video. But now I can do it without having to row reduce a matrix. I can do it just by using the formula. And if you take a look at this, this is essentially the projection formula, right? The thing that we saw looks like a projection formula. So how does that tie in? I think we can try to answer Erica's question. All right, let's see. Let's and they just happen to be the formulas for the projection, and that's how you get to project onto that. Okay. All right. And so according to this, we have this projection vector. Now, this orthogonal projection explanation, I tried to get it from the book, and it got a little confusing. It probably got more confusing than what it needed to be. So the bottom line is that alpha is the scalar that you multiply u by to get the length that you're looking for. So in this picture, why can't I draw? In this picture, you multiply u by alpha to get that length. And so somewhere over here, y hat is equal to alpha u somewhere. It doesn't say that. But y hat is equal to alpha u. Because you might be in 3 and 4 dimensions, and then that could get a little bit more difficult to deal with. Okay? And I think the point here is that in the beginning, you would know u and y. You know what u and y are, and then you want to find z. And for you to find z, you actually need to find y hat first so that you can find z. So why is z important here, you think? What? It's perpendicular to the u vector. U and z are orthogonal. So what we're going to do is we're going to create a set of orthogonal vectors. We're going to start with one vector, and then they're going to give us a second vector. And if that vector is already orthogonal, great. If it's not orthogonal, then we're going to find an orthogonal vector. So we'll find, first we're given u, and then they give us another vector y, and then we have to find a vector that's perpendicular to u that's going in the general direction of y. And after that, they might give us another vector, and we want to find another vector that's perpendicular to u and z. And so we'll build on that in the next section. That's what we're going to try to do, is build a bunch of orthogonal vectors from a set of vectors that may or may not be orthogonal. Okay, and I'll bring more sticks next time so that we can see it. So I gave this as an example. And then an orthonormal set, so this is a new definition. An orthonormal set is a set that's perpendicular, and they're also all of unit length. So ortho, perpendicular, normal, unit length. Maybe I should write that down. Orthonormal. So because an orthogonal set forms a basis, then an orthonormal set would also form a basis. And it turns out that it's always nice to deal with an orthonormal set, regardless of where you are. Yeah?
Would an orthonormal set produce like a plane that basically has like a new origin, since they don't have a...
Yeah. So if that's if we want to think about this as being in R2 or R3, actually in Rn, yeah, you can think about it that way. Again, for those people who have taken Calc 3, some teachers go over this thing called the Frenet frame. Does that sound familiar? The NBT frame. NBT. TNB. TNB. Yeah, TNB. T is a unit tangent. B is the binormal. No, N is the normal. B is the binormal. So in that order. Okay. So this example was an easy example because everything's already orthogonal. To make it an orthonormal set, I just have to normalize everything. So by normalizing everything, then everything's of unit length. Okay. So based on the quizzes, and this is this morning before only half of you guys have taken the quizzes, some of the last question is asking you what else is not clear. So let's take a look and see what else isn't clear. I need more work on orthogonal projection and the idea of an orthonormal set. So I think we got a little bit more practice on that. Still confused about how you write X as a linear combination of orthogonal vectors V1, V2, V3. Not exactly sure. I'm not sure exactly why, but I guess I'll find out in the quiz. So the projection of vector onto another vector is clear, right? So I guess if I want to comment on this, you can write X as a linear combination of orthogonal vectors. So X is equal to C1, V1, and let's put highlights on the vectors. Whoa, why did it turn black? C2, V2 plus C3, V3. So to write something as a linear combination of V1, V2, and V3 means I have some arbitrary constants. And to say X is a linear combination of these things is to say this, essentially. And now, if V1, V2, and V3 are all orthogonal, we can use Theorem 5 to figure out what C1, C2, and C3 are fairly easily. Yeah? Or that's what orthogonal means. They have to be perpendicular to each other. They don't have to be perpendicular to X. No. Yeah, they just need to introduce a new dimension. But, you know, in what we're studying, we're interested in making sure that they are orthogonal. Yes. Right, because there's perpendicular, which makes it nice, right? Because if we have to do dot products of things, then because these are all orthogonal, then the dot product is going to be 0. And even nicer is that if they all have unit length. If you could think about it that way, yeah. Yeah. If they are orthogonal, they're linearly independent, yes. Well, we'll just say, since we're just staying in Rn now, let's say orthogonal and perpendicular are the same. Okay, last time I didn't want them to be the same because we can't, you know, perpendicular in polynomials is weird. But if we just forget about talking about polynomials and stick with Rn, then orthogonal means perpendicular. Yes. No. All right. This is an interesting clarification. So orthogonal set of vectors where each pair of distinct vectors have a dot product of 0. So all vectors in that vector set are perpendicular to one another. So this is correct, right? A set of orthogonal vectors is linearly independent. Therefore, a basis of the subspace of that set is a part of. The set would be called an orthogonal basis because it's a basis and it's also an orthogonal set. That's true. I'm not quite sure I understand Theorem 5 correctly. It simply states that for some orthogonal set, the basis subspace is the equation. So this is not the basis of the subspace. Can be used to find constants in the equation and find any vector in that subspace, since any vector within the subspace is a linear combination. Yeah, so I wouldn't say that this is a basis for a subspace, but the basis for a subspace is already given, V1, V2, V3, and all that. And then the C sub j would just be the weights. So these are the weights. Weights with the basis. That's what this formula tells us. It gives us the values for the weights. And the values for the weights really just tell you how far to go in the X or in the V1 direction, how far to go in the V2 direction, how far to go in the V3 direction, if it's an R3. Orthogonal projection seems pretty similar or identical to the vector projection from Calc 3. Projecting A onto a plane, a subspace, means creating a vector B. So this is true for those people who have taken Calc 3. It's just projecting. In Calc 3, we just stick to projecting a vector onto another vector. But now, here, we want to be able to project a vector onto a space. First, a linear space, which is what they talked about, and then we'll see that we're actually going to project onto a plane also. So the projection onto a plane is going to be important. For Calc 3, that's a little bit more difficult to do, but we're going to find formulas in this class to be able to do that here. And then an orthonormal set is just an orthogonal set of unit vectors or vectors with magnitude 1. Correct, each of those vectors will have magnitude 1. Confusing the following orthogonal sets. I could not understand the inner product necessarily making orthogonal sets. Well, the whole idea behind the inner product or the dot product is that the dot product of two orthogonal vectors is 0. So you would just check to take the different vectors in your set, dot them to see if they're equal to 0. I was able to understand a scalar projection, but the vector projection, but I wasn't able to see them graphically. So we kind of did this little graphic thing over here, so I hope that cleared up a little bit, whoever posted this. No, somebody posted this. We're all good. Actually thought of watching the video on my own for okay, a lot. Concept isn't entirely clear. I mean, relationship between orthogonal vector set or orthogonal projection related subspaces. Also, visualizing these, at least when possible in 2D, is a bit confusing. Significance of these calculations, why they're done, or prepared formulas, so it makes sense. So I think the thing that we did, here in 3 dimensions is like an it's essentially like this drawing in 2 dimensions, where it's just a projection. Okay, so I hope that makes sense to whoever posted this. Everything seems to make sense so far. Can we go over more detail? The proof for Theorem 5. Oh, so the proof for Theorem 5, let's take a look at Theorem 5 again. So the way they prove Theorem 5 is what is Theorem 5? So this is the formula that they say, right? So what did they say? Oh, so what they said was, if you start off, so you have these vectors. Let's say we were in R3, we have these vectors, U1, U2, etc. And then you have Y, the Y vector. So what they do is they take the Y vector and then they dot it with U1 just to see how it would look like with a U1. And what happens here is that they replace the Y with this thing, C1, U1 plus C2, U2, all the way up to CP, UP, dotted with U1. And then there's a distribution formula, right? Or property, C1, U1, dotted with U1. What's happening? Plus C2, U2, dotted with U1, plus plus CP UP dotted with U1. And do you see something happening here that we can simplify? Yeah. We're kind of being projected onto U1. But what can we say about U1 and U2 and U3? Yeah.
Since we're dotting it with itself, like the dot product goes along on the left side, I guess, 0.
Yeah. So these are all equal to 0. Everything there. Why? Because we have an orthogonal set. U1, U2, U3, all the way up to UP are all orthogonal to each other. So all those are going to disappear. So then you have C1, U1 dotted with U2. So that's what this is equal to. Right? And so if you solve for C1, that's equal to Y dotted with U1 divided by U1 dotted with itself. So if you do that for the rest of them, the same thing will happen, and then here's your formula. It's pretty cool, huh? So that's a proof of that. Any questions? All right. Yes. Oh, sure. Yeah. Well, I would like to have seen more, but I guess if I've seen more, then we could have tried to consolidate it to the things that people didn't understand. But this is based on at least the people who took it before 9 o'clock today or whatever I started to look over this. So if you took it after that, you might still have some questions, but if you got an answer here, great. If it didn't, then I'll try to respond back. Okay, so what I wanted to do is have you guys work in groups to answer a couple of questions. I took some questions from the book, and I want you to give them a try. I took them from section 6.1 and 6.2, but I think I want to start with 6.2 since that's kind of what we've been focusing on. And then if we get done with that, then we go back to section 6.2. I didn't highlight, maybe before we get started, I didn't highlight Theorem 6 too much. And so maybe that's why nobody really asked about that. I guess we weren't quite done here. Oh, there was a definition from before that says that if U, a matrix, and they use capital U for matrices, if a matrix capital U had columns that are orthonormal, then it has this special property where if you take the transpose of that, dot it with itself, or multiply with itself, you get the identity. And so in this, this was an example that I don't know if I did in the video. And then the other part of this is that there's this other theorem that has more information about the matrix. So the second part here has information about the matrices, and you're just to verify a few things. So let's get into groups. I'm not gonna, you guys put yourselves into your own groups. Let's have groups of at least 2 people and at most 4. Okay, so stand up, get into groups, and we'll do some group work. And I want you to attack some of these problems, and then if you get done, then go back to 6.2.